Hey everyone, welcome back. Last episode, we talked about how to build a gradient descent algorithm from scratch on a simple toy data. So if you look at the screen, for example, we build a toy data that's called an X that's generated by some random number. And we build a theoretical model. We have theta 1, we have theta 2. We know exactly what these numbers are. They are randomly generated, add a little bit of noise. It's a linear model. Specifically, we have y, and then we have this model defined as the constant term theta 1 plus theta 2, which is the coefficient. And then on top of that, we have x. So with that being said, we talked about the gradient descent algorithm. Specifically, what that's doing is, based on this x, we initialize some sort of parameters, theta 1 and theta 2. These sets of parameters give us some sort of educated guesses. Now, of course, in the beginning, the educated guess is not going to be accurate, it's not going to be precise. So we have this loss function that's defined as a mean square error, and specifically, it's an L2 loss. So we're taking educated guess, we're comparing that with your y, which is a real value, we take a square. So something like that is definitely interesting because it allows us to take the gradient of the mean square error. And this gradient tells us precisely what we should do to update the parameters. And hence, the idea of gradient descent algorithm, it's built on your gradient kept decreasing over the time. So we run through this code. It turned out that let me set this to 1,000, and then let me set this eta to 0.1. We can get some sort of theta that is very close to the theoretical value. Here I have a 1.98, I have a 3.02 for theta 1 and theta 2 respectively, and the theoretical value are theta 1 and theta 2, which is 2 and 3. So it's close enough, but it took us 1,000 iterations, and this theta is 0.1. It's relatively small. Now, with that being said, what could go wrong here, right? This 0.1, it's because we read the textbook, we learn from the class, we've done this experiment before, we've had all those prior ideas, we've had all those prior experiences. That's how we know this learning rate, eta, is 0.1. Given the new data, we have a new sets of x and y. We don't necessarily know what's the optimal learning rate, eta. So we're gonna have to try it. For example, maybe you're gonna hit 1, right? And then you run that, maybe it's gonna work, maybe it's not. Then in this case, it's not gonna work because it explodes. What if it's 0.6? Let's run that. Maybe it works. Let's check it out. -3 to the power of, okay, that's obviously not right? It's completely wrong. What if I drop a little bit more? Let's say 0.4. I run that. Okay, now it's getting a little bit closer. So that's the problem of learning rate. It cannot be too large, and it probably shouldn't be too small either, right? Let's say, what if I have 0.000001? Then I don't know if that's going to converge. See, this result is -0.88 and -0.29. So that's no good either, right? There's that sweet spot in between that we need to play around the algorithm to find it. Same with the iterations. Let's say we found eta to be the best at 0.1, all right? And it gets us the results that's close enough. But we don't necessarily know this 1,000 in this iteration is the best, right? Ideally, if everything goes perfect, if it's in the dream world, we have this an iteration to loop like a few times, and we're happy with the results. That's fast and furious. So that's definitely something that the programmers will love to see. But that's unfortunately not the case. If you have 1,000, sure, it worked. But what if I change to 10, right? That's probably not going to work. So the result is 2.23 and 2.8. It's already much further off than the original results. And I have to change this to 100, and probably it's going to like a slightly better 2.05 and 2.96. And now I have to change this to 1,000 to get slightly closer. So essentially what it's saying is the iteration If it's too small, it's probably not going to work because it doesn't converge. You're not at the optimal point yet. If the number of iterations is too large, sure, eventually you may be able to hit the optimal spot. There's no guarantee. And what if the data is huge? What if the data is not 100? What if data is 10,000 rows? Then what are you going to do, right? So because of all these problems, fortunately, we have another algorithm called stochastic gradient descent. And specifically, I'm going to write this out here. The motivation is exploding or vanishing gradient problem. And then the second part is computation time. And then, of course, there's more, but I'm not going to spit out each one of them. I'm going to take these bullet points as the major motivator, and we're going to take it from here. So in terms of a stochastic gradient descent, we are really talking about a gradient descent, but in a stochastic point of view. What do I mean by that? Stochastic is essentially saying random, okay? So what that means is in my gradient descent algorithm, I'm going to inject some sort of randomness. Hopefully that will help us bypass some of these plateaued area in the loss function that perhaps the conventional gradient descent is not able to surpass. So let's code that out. First, we have parameters. So we're gonna say n epoch, and we're gonna set to 20, something small. On top of that, we have two smaller parameters to help us set the course, T0 and T1. And I'm gonna set that as 5 and 20. So here we're gonna call it the hyper parameters for learning rate. Okay, boom. All right, so with the parameters being set, I need some sort of a function that's called learning rate. Now this learning rate takes an input of t, okay? And you can simply think of this t as an index for a particular step within some sort of for loop. Each step in this for loop, we are changing this learning rate. So essentially, in the original algorithm, this learning rate, eta, is not changing, yeah? So in this for loop, I'm not changing eta, okay? Eta is 0.1. If eta doesn't work for 0.1, I have to run this entire for loop, change to 0.2, and then we're gonna try again. Here in stochastic gradient descent, we are constantly updating the learning rate eta at each step of the for loop. So here we're gonna return some sort of a fraction, t0 divided by t plus t1, all right? That's gonna be the learning rate. I've seen some papers adjusting this formula here, adding some coefficients or changes form. They're essentially expressing the same idea, which is to search for the most optimal learning rate that you can use in your gradient descent algorithm. So with parameters, with learning rate being defined, let's talk about the actual algorithm. We're going to initialize data to be some random number, right? NP random number. I believe that's normal, and that's going to be the size 2 by 1. Okay, so let's start our for loop. For epoch in range n epochs, we have another for loop. For this is going to be a particular index of the data. For I in range m, and this m is going to be defined up here, which is consistent with this dimension of the data generated up front. Okay, so with each epoch, within each I, we are talking about updating parameters, but we're going to inject some random noise. So we're going to call something like a random index. We're going to define random index as np dot random integer, and then we're going to say m. So within the range of m, we pick a random integer. and we're just going to call that random index. And this random index is going to allow us to define a new x and a new y. I'm specifically going to call it xi and yi. Why it's called x and yi is because we want this to be a particular index, a particular observation of your data, xb. Xb is defined up here. Specifically, it's a concatenation between one's column and your x. Okay, so that's going to be random index to random index plus 1. Here is going to be y random index to random index plus 1. This bracket random index colon random index plus 1 is essentially talking about this xb, and we're extracting the observation according to this random index. And the convention for Python is the index actually does not include the first number that you add in. For example, let me get out here, let me add a coding box. Here I have xb, right? I can take a look from 0 to 5. So that's going to give me the first one all the way to 4th. Okay, so if you take 0 plus 1, it's just going to give you the first one. Because if you don't do that, let's say I get rid of this 1 here, it will actually give you the empty array, and you don't want that. Well, this is why we add a plus 1 on top of this random index colon random index. Now, with that being said, essentially all we have done here is we have a for loop. Within this for loop, we have a nested for loop, and then within the second nested for loop inside, we're defining a random index, and according to this random index, we have a new x, we have a new y. Now, it's pure math, right? We're talking about taking gradients of this thing. So we're gonna look at gradients. Here we have a different algorithm. Specifically, we have a different formula. Let me write it here. New gradients, okay? And we're talking about taking partial derivative, okay? That's partial theta of some sort of loss function. And here we're gonna have essentially our mean square error. But the problem is this is actually just one observation. So originally, if you look at this formula, there's an m. Right now, the m actually just disappears because it's just 1. We're taking one number here, right? This gives us one number. So this is just gonna become 2 sum. We have our educated guess, which is x theta minus y, and don't forget a chain rule. So x come out, boom. That's actually going to be our new gradients. So here we're going to code that part. 2 times xi, which is defined here, and then we do a transpose, a dot product of whatever's inside of the parentheses. So we're going to say xi dot theta minus y. That's going to be your gradients. And last but not least, we're going to update our parameters. So we're going to say theta equals to something. But before we do that, we need to update our learning rate because this theta here actually requires us to update our learning rate. So here we're going to have some sort of eta times gradients. Gradients is already defined. We have not defined eta. We're going to do that right now. Eta, we're going to call this learning rate function. And precisely in this input of the learning rate function, we're going to give it something that is changing every time, right? So we're going to give it epoch, right? That's going to be telling us which step that it is at here, times m. M is going to be a total range. So this M does not change. This epoch changes every time. So, and we also have this. So this epoch, it changes every time, but this M, it's fixed. On top of that, we're gonna plus I, just to give it a little bit of a randomness that's from the second loop that's inside. And we're gonna run it. There's some problem with my gradients. And let me check my math. So this is going to be xit, that's gonna be transpose dot product of xi dot theta, and this is the mistake. So this y is wrong because this y is actually the dimension of like 100 observations, right? We don't want that. That's not going to work. We need this yi here because this yi is defined as just one index. So it's just one array of number. Now that's going to work. Boom. All right, let's print out theta. So as you can see, it's much closer to the actual theoretical value 2 and 3 much faster. Here we only have 20, right? Now, there's somebody may argue, here, what's the time analysis? The time analysis is actually O of n epochs, okay, plus m. It's not strictly speaking much faster than the gradient descent. I'm gonna write it here. Time is going to be O(n) iterations. Okay, so that's actually gonna be just one loop of n iterations. Here, actually, I think I made a mistake. This is gonna be time. So each epoch, we run each I from m. So the total round of loops for both 2 for loops, that's going to be n epoch times m. So that's not strictly much faster. But usually the idea is that if you have n iterations to be 10,000, 100,000, then what's happening is this will be much faster because this n epoch, typically it's a very small number. And I would say from experience, it's much smaller than this total number of iterations here. So what I'm gonna do is I'm gonna put a remark and I'm gonna say typically n epoch is much smaller than this. And n epochs is in stochastic gradient descent versus n iterations is just gradient descent. And sometimes people call it batch gradient descent. Hopefully in this episode, you get a little bit good grip of what is a gradient descent, what is the stochastic gradient descent, specifically what's the pros, what's the cons. And then on top of that, we talk about time analysis. We can also get into space analysis, but it doesn't make too much sense of talking about space because technically speaking, we're not trying to memorize a whole lot of things. Each step of both algorithms, we're updating theta as it goes. We're not trying to memorize all of the thetas. So in terms of this particular exercise, the space is going to be the same. So with all that being said, let's wrap up this episode. I hope you like it, hope you enjoy it. If you want to support the channel, give it a like. I really appreciate that. And hit the subscribe button, and I'll see you in the next episode.